In this video, we incorporate our substitution and elimination skills to solve systems of inequalities. Let's get started. So recall that whenever you have a system of inequalities, what you're really trying to do is first find your points of intersection, but then shade the appropriate region. Now that's the extra step that usually causes some problems for students. So first of all, you have to recognize when you have this situation, right? Notice in the example on the screen, we have a system of two inequalities. Now I say inequalities because I don't see the equal sign in between my variables. I see in the first case the greater than or equal to symbol, and in the second case the greater than symbol. If you see any of those four symbols, greater than or equal to, less than or equal to, greater than or less than, you're talking about an inequality. And that means when you graph it, you're not just talking about the actual line itself, those points, or the actual parabola or circle itself, but rather all points on or above that graph, or on or below that graph. If it's strictly greater than or strictly less than, you're just talking about the points above the graph or below the graph. So we have to really watch carefully where our solution regions are. So let's begin by noticing that if we have the or equal to symbol, we'll be talking about a solid structure, a solid line or a solid parabola, circle, etc. On the other hand, if we have strictly a greater than arrow or a less than arrow with no equal sign, you're talking about a dashed line or a dashed curve or a dashed circle, meaning that it's a boundary point, but it does not include the points on that graph, on that structure as part of the solutions. Okay, so that's the first thing. Recognize what kind of graph you have. Secondly, shading. How do you know where to shade? Well, you could have an instinct above or below, but instincts need to be proven in math. You need to actually justify your answer. And the way you're going to do that is by picking a point that is not on your graph, not on the line, not on the parabola, and seeing when you plug in that point if it's true or false. If it's true, shade where that point is. And if it's false, do not shade where that point is. So we're going to demonstrate that in a moment. And finally, find your points of intersection like we did in our previous videos using substitution and or elimination. Once you've done that, you're going to label your vertices that trap the shaded region. Those vertices are your points of intersection, not just random points. This is points of intersection, which do in fact trap your shaded region. Okay, so let's begin with this example. We have 3x plus 4y is greater than or equal to 12. So we notice that this first equation, or inequality to be more specific, 3x plus 4y greater than or equal to 12, is linear. So I would call this like line 1. So for line 1, I could graph that line by either getting its intercepts, letting x equal 0, getting y, and vice versa, or by getting y by itself and using the slope-intercept form. Feel free to graph it in either of those two ways. You'll still get the same line. I'm going to use the intercept approach in this method. So I'm going to say when x equals 0, what happens to y? Well, if x is 0, I would have 3 times 0, which is 0. And then I would just have 4y equals 12. What would y have to be? If x equals 0, what would y have to be? 4 times what gives me 12? 3, right? So 0, 3 would be my y-intercept. 1, 2, 3, that's a point on the graph of the first line. 0, 3. Okay, now that I have that point, let's see if we can get another intercept. Another intercept would be found by letting y equals 0. So we'll find the x-intercept this way. If we let y equals 0, 4y goes away because 4 times 0 is 0. I would just have 3 times x must equal 12. So what would x have to be? 3 times what equals 12? It would have to be 4, wouldn't it? So the x-intercept would have to be 4, 0. 1, 2, 3, 4 to the right of the origin. So 4, 0. So now I've graphed 2 points on the line represented by this inequality. Now would this line be a solid line or a dotted line? It would be solid, right? Because of the or equal to. So with a ruler, you draw your best line for sure. And I would have something like this without my ruler. Here we go. There's line 1. I'm going to label him as such, L1. And he would continue with the same, that's rough, the same rate of change, same slope as you move forward. If it's truly a line, you have a constant rate of change, a constant slope. In this case, you can probably tell what the slope is, right? I went from this point to this point, 0, 3 to 4, 0, by going down 3 units and right 4 units. So down, that's negative 3, and right, that's positive 4. So if you had solved for y instead, and you had y equals a slope of negative 3/4 as your m times x, and then you added your y-intercept of 3, you would get the same graph. Okay. So now that we have the first line, the next question is, would I be including all the points on the line and shading below it, or include all the points on the line and shade above it? Well, it might appear to you obvious just by looking at the inequality symbol. Whenever people see greater than or equal to, you're inclined to think it's always going to be above. But you want to double check that, triple check it if you need to. And that involves using test points. So to use a test point, you're going to pick a point that's not already on your graph. So my favorite, you're going to notice that your professor loves this particular test point. My favorite test point is always 0, 0. If it's available, I'm going for it, because 0, 0 is the easiest to manipulate, right? You can stick a 0 and a 0 in and everything goes away quickly. If it wasn't available, like let's say that your graph had gone through 0, 0, your line had been going through that origin, you'd have to pick another point. Maybe I'd pick 1, 0 or 1, 1. Pick easy points. Make it easy on yourself. So that means that if I plug in 0 for x and 0 for y in the first inequality, we have to ask ourselves, is it true or false? That will tell me whether or not I should be shading there. So 3 times 0 is 0. 4 times 0 is 0. So now I have 0 plus 0, which is 0, is greater than or equal to 12. And the question is this true or is this false? Is 0 greater than or equal to 12? True. So should I include the point? Yes. So since it's true, we include your test point. If you're including your test point of 0, 0, are you shading above that line or are you shading above, sorry, I said that twice. Are you shading above that line or are you shading below that line? Correct, you are shading below this line. So I will be shading below line 1. Okay, now that I have that, you are welcome at this point, if you really like to be artistic, you could go ahead and actually show that. Like you could color in everything below and on that line. I wouldn't recommend it. My preference as a person doing these problems is to always shade my graph at the very end. So I write a little note, shade below line 1, and then I talk about where to shade in relation to my next constraint or inequality. And finally, I'll shade together where they both are happening at the same time. But if you like to do them one at a time and then just see where the overlap is, you're welcome to do that, but you might have some erasing to do, so just be aware. Okay, let's take a look at our second constraint. Our second inequality is x minus y is greater than 4. So to recognize first that that's a line, that's your first step. This is line 2, right? So for line number 2, we have x minus y is greater than 4. We could either graph that line by getting y by itself. If you would do that, I would recommend keeping y on the left side of the inequality. That's usually the safest. But keep in mind, if you divide by a negative or multiply by a negative, you must flip the arrow. So be careful if you choose that path. Otherwise, if you're like me, you're going to get the intercepts by letting x equal 0 and then by letting y equal 0. So go ahead and do it either way and see if you can get 2 points on the line and then graph this dotted line because it's not equal to. So when you did x equaling 0, that would mean that negative y gives you 4. So what would y have to be? Negative 4. Yeah, the opposite would be negative 4. So 0, negative 4 should be a point on the second line. 1, 2, 3, 4. 0, negative 4. Point on that second line. I'll go ahead and write that in a darker color blue because it's a little hard for some of you probably to see. Let's get that fixed. There he is. 0, comma, negative 4. Okay. All right, so that would be our 1 point on our second line. Now for the next one, if you let y equal 0, we should get our x-intercept. If y is 0, you would just get x minus 0 gives me 4. In other words, x equals positive 4. Oops, I used the eraser as my pen. I wouldn't recommend that in your test. That would not be good. So we're going to make that a 4. Okay, 1, 2, 3, 4. Look what I just stumbled on. I accidentally landed on another point of intersection, didn't I? I think this may have happened in our previous video in one of our examples as well. So you don't always get this fortunate or lucky, but it turns out we've just found one of the places, looks like the only place if they're both lines, where these two lines come together. Okay, now these two lines, I need to now draw a line through it. The second line should be dotted, indicating that the solutions will not be on that line, but rather that is a boundary. Okay, now this is our second dashed line, is line 2 there, L2. As far as shading is concerned, we now need to think about where makes the most sense to shade. Where makes the most sense to shade? Well, we need to know where line 2 shades. Do I shade above it or do I shade below it? So remember the idea of test points? Pick any point which is not already on your graph. 0, 0 works for me. That's not on the graph, is it? So if I put 0, 0 into line 2's inequality, we would be noticing here that for line 2, I would have 0 minus 0 is greater than 4 when I test the point 0, 0 in line 2. That would be saying then that 0 has to be bigger than 4. Now, is that true or false? Is the number 0 bigger than the number 4? No, that's not true. That's false. So if you get something false, that means we do not include the point 0, 0. So if you do not shade there, that means we cannot shade where? We cannot shade above that blue dotted line, line 2. So we must be shading below line 2. So if we're shading below line 2 so that we don't accidentally cover the point 0, 0, now we know what's going on. I'm supposed to be shading below line 1 and below line 2 at the same time. So if you think about what that would be, below line 1 and below line 2, where would we be? Well, wouldn't we be in this region? Below line 1 and below line 2? So any point in that region, which is mostly in quadrant 4 and a little bit of quadrant 3 as well over here, we would be having all of our solutions for this system. So the places where this is true, where you're satisfying both the first constraint and the second constraint, would be any points in that shaded region. Now, the last thing you want to do when you're trying to answer a question about systems of inequalities is you want to make sure that the reader knows what your vertices are. The vertices will become really important when you start applying these graphs, these systems of inequalities, to real-life situations, because those vertices are typically called your optimal solutions. In linear programming problems or operations research. It's a very lucrative field if you go on in math. Operations research involves these types of problems, these inequalities. So if we wanted to find the vertices, what would I need to do? Well, I first need to find my points of intersection. I just so happened to stumble upon our point of intersection in this problem, which was 4, 0, because that was visually where the two graphs met. But typically to find these, you have to do substitution or elimination. So if you were trying to check yourself to do it the long way, you would have taken the first line as an equation, 3x plus 4y equals 12. So notice I made it an equation. And the second line as an equation was x minus y equals 4. And you could solve this by substitution or elimination until you get your solution of 4, 0. And you can check right now that that makes sense. If you put in 4 for x into each equation, you should get that the only way that works is if y is 0 in both equations. All right, so once we have the point of intersection, in this case just one if it's just two lines, but when it's parabolas and circles and other different manipulations of graphs, then you're going to potentially have multiple places where they intersect. But once you found all points of intersection, you want to ask yourself, is that one of the vertices? Again, to be a vertex, to be one of the vertices, you must be a point of intersection which helps to trap the shaded region. Does that point help to trap the shaded region? It does, in fact. It's that tipping point, right? So I would say yes, the only one of the vertices that are present in this case is the point 4, 0. So that would be the only one of our vertices that is present in this problem. It would probably be our optimal solution for this problem if you're going forward to apply it later on. Okay, so at this point, let's just review the steps, and then you're going to try one on your own. We first recognized whether or not our graphs were going to be solid or dotted based on the inequality. Does it have an equal sign or does it not? We second then tested whether we were going to shade above or below each graph after you graphed them, of course, by using a test point that was not already present on the graph. If it was true, you shade where that point is. If it was false, you shade where that point is not. Then we found our points of our points of intersection by using by using substitution or elimination. Now sometimes you get lucky, like we did in this one, where they actually visually are shown on the graph 4, 0. Otherwise, you'll need to use substitution or elimination. And finally, once you have your points of intersection, make sure you label correctly your vertices, which are those points of intersection which do in fact trap the shaded region. They will be very important going forward in operations research. Okay, so let's take a look at an example for you to try on your own. As always, it's really important for you to pause and try it to see how you're doing. Example 1 says, sketch the graph of this system of inequalities. Be sure to label all vertices of the solution region. The first constraint says x squared plus y squared must be greater than or equal to 9. The second constraint says x plus y must be less than or equal to 3. So we have to satisfy both constraints at the same time. Where would my solutions be? Well, first you need to recognize what type of graphs you're dealing with. Are they dotted? Are they solid? Are they lines? Are they circles? What are they? For the first one, what do you recognize? I think we talked about it in our previous video. This is that's right, a circle. What is the center of this circle? 0, 0, correct. And its radius? Yep, r is 3. So we've seen these before. Because the standard form x minus h squared plus y minus k squared equals r squared is obviously what's going on here. And our hk must be 0, 0, and the square root of 9 must be 3. So if you were to sketch this circle, would it be a solid circle or would it just be a dotted boundary of a circle? Solid is correct because it's a equal to. So I go from the origin, my center, 1, 2, 3 units up. That's a location of 0, 3. 3 units right, that's the location of 3, 0. 3 units down, that's the location 0, -3. And 3 units left, that's the location of -3, 0. Okay. Draw your circle, hopefully better than your professor will. Here we go. There's a little arc. Oop, that's a rough one. And there's another one. And there's another one. Okay. So you have a basic idea of what's going on here. You have a solid circle who's centered at 0, 0 and has a radius of 3. Okay. From there, you need to talk about shading. Would I be shading inside of the circle or beyond the circle? Remember, because it's a solid circle, the solutions would also include the points on the circle itself. Okay, so to figure out where to shade, we use a test point. So we need to pick any point that is not already on the actual circle itself. So notice I could pick the origin. You might think, wait a second, isn't the center at the origin? True, but the center is the point from which all points on the circle are equidistant. They're all the same distance. The center is not on the circle. The center informs or determines the circle. So we could use 0, 0. Okay, it's not on the circle itself. Let's do it. 0 squared is 0, plus 0 squared is still 0. Is that greater than or equal to the number 9? In other words, is 0 greater than or equal to 9? Nope. So since that is not true, can I include the point? No, I cannot. So if I cannot shade where 0, 0 is located, which is inside the circle, I must be shading outside the circle. So I'll be shading outside my circle. And then now we need to talk about what the other constraint's doing, what it requires. So let's head over to our second constraint. What type of graph are we looking at? We have x plus y must be less than or equal to 3. That's a line. Good job. To graph that line, feel free to get y by itself. That's probably the way most students would do this problem. On the left side, you keep y right where it is. Y is less than or equal to 3 minus x, or negative x plus 3. Or you could have done the intercept method. Let x equal 0, let y equal 0, find your x and y intercept. You'll get the same 2 points in this case. So if you were graphing it using the y equals mx plus b approach, we would notice that the slope here is -1, or down 1 and right 1, or up 1 and left 1. So both of those mean the same thing, up 1 and left 1. Also, we notice that our y-intercept is the number 3, isn't it? So we could start at 3. Ooh, I just landed at a point of intersection, didn't I? There's a point of intersection. I'm just going to write it down right now. The 0, 3 is on both the circle and this line. So I just stumbled upon that. That's very nice. Okay, now from 3, the y-intercept, I use my slope to go down 1 and right 1. So down 1 and right 1, and I could keep going like that, down 1 and right 1, down 1 and right 1. I think I just hit the circle again. You might see where it is. Down 1 and right 1, down 1 and right 1, etc. And then you could draw your solid circle, right, because it's or equal to. I said circle, I meant line, solid line. All right. So there's our solid line. Okay, so we have our line, and it looks like we found another point of intersection. I think it's at 3, 0. Do you agree? Maybe your graph looks different than mine, so maybe we shouldn't trust my graph. Okay, so we'll come back and double check that. But it appears to be there. Okay, so we'll know for sure in a moment. Have no fear. But let's continue with the problem where we talk about where to shade, right? We need to test our line. So we pick a point that is not on that line. Guess who I'm going to pick? Yeah, 0, 0. Let's test 0, 0 again here, but this time for the line. If we put in 0, 0, what would our linear inequality be? It would be 0 plus 0 must be less than or equal to 3. So is 0 plus 0 less than or equal to 3? Well, that would mean 0 is less than or equal to 3. Is that true or is that false? Is 0 less than or equal to 3? It is less than 3, so we'd say this is true. I would include 0, 0. Where is 0, 0 located in regard to the linear inequality, the blue line? It's below it, isn't it? So I will be shading below the line. So now I know I'm shading below my line, and at the same time as shading below this line, I need to be shading where? Outside the circle? Okay, so if you're shading below the line and outside of the circle, below the line would be any point here in this region, right? But not inside the circle. So that would mean any point out here is fine in this area of quadrant 2. Any point out here is fine in this region of quadrant 3. Any point in here is fine in this region of quadrant 4. But on the circle itself, inside the circle itself, not included. On the circle out here, definitely included, right? On the line out here, definitely included. On the line up here, definitely included, because it was or equal to. So any of those points that are on that part of the circle or that part of the line, just basically not in the interior there and not in the quadrant 1 part, and below the circle and below the line, outside the circle and below the line would be our solution region that we're looking for. So when they say sketch the solution region, they include we mean you must include the shading. We must know what points would satisfy both constraints at the same time. And any point in those locations does satisfy both constraints at the same time. To finish the problem, you need to clearly label your vertices. So what are the vertices again? They're the points of intersection which clearly trap your shaded region. Well, the only points of intersection appear to be here and there. So let's verify, were they in fact 0, 3 and 3, 0? Well, to check, we would have done substitution or elimination. And you can check our previous video to go through that process again of how that worked. I would have probably done a substitution here because there's no two like variables on top and bottom to eliminate. I have the system here of x squared plus y squared equals 9 and x plus y equals 3. So if I was attempting to solve this by substitution, I could isolate, let's say, x in equation 2 so that x equals 3 minus y. Then I could substitute for x into equation 1. I would end up getting something like 3 minus y squared plus y squared equals 9. So I get a quadratic equation, putting it in descending order, y squared. When I then go ahead and FOIL 3 minus y times itself, you'll end up getting a negative y times a negative y, which is a positive y squared. You'll end up getting a negative 3y 2 times, which is a negative 6y. And you'll end up getting positive 3 times 3 is positive 9, equaling this 9 from the other side. The 9s will cancel when you subtract 9 on both sides. And if you add y squared plus y squared, you get 2y squared minus 6y equaling 0. Now at this point, if you were to continue with the problem, you're probably wondering, how am I going to solve this? I don't have a trinomial. But you could factor out the 2. You have 2 times y. You could actually even factor out the y, couldn't you? 2 times y in front. You would have y minus what? 3 equaling 0. And now we're back to that 0 product rule. Either 2y equals 0 or y minus 3 equals 0. If 2y equals 0, then y would have to be 0. And if y minus 3 equals 0, y would have to be 3. Aren't those the two locations that we have on the graph? When y equaled 0 and when y equaled 3? When y equaled 0, we're either here or here, and we're on both of them, x is 3. And when y equaled 3, we're either, well, we're only here, aren't we? And that's when x equaled 0. So it does, in fact, appear to be correct. You could then plug in those values into your smaller powered equation. So if you plugged in your 0 for y, you'd have x equals 3, which is what we expected. And if you plugged in 3 for y, you would have x plus 3 equals 3. So x would be 0, which is what we expected. So yes, our 2 points of intersection were, in fact, the ones that we thought they were, 0, 3, and 3, 0. Finally, are those your vertices? Well, yes, because they are the only points of intersection which appear to be trapping the shaded region, right? If there was another point of intersection that was not trapping the shaded region, then we would say, no, that's not a vertex. But in this case, they're both also trapping the shaded region. So this time your vertices are still those same 2 points. Okay, that was a lot. See if you can try example 2. It's a little cleaner by yourself. Here we go. Example 2 says the same thing. Solve the system and shade correctly. Y is greater than or equal to x squared minus 2 for your first constraint, and y is less than x plus 4 for your second constraint. Okay, let's see how you did. For your first constraint, what shape or what graph were we dealing with? Was it a circle? Was it a line, a parabola, or something else? It was a parabola. Well done. So we had a parabola for our first constraint. Was it a solid parabola or was it a dotted parabola? Would I be including the points along the parabola or not? I would include them. It's solid because of the or equal to. This parabola has been shifted how? Down 2? Yep. So that -2 meant down 2. So my 3 key points, after shifting it down 2 units, would be where? Instead of 0, 0, down 2 units, I'm at 0, -2, aren't I? Instead of -1, 1, instead of -1, 1 up here, down 2 units, I'm at -1, -1. And you could do that just by subtracting. 1 minus 2 is -1 from the y values. Instead of 1, 1 up here, I'm down 2 units at 1, -1. And I could also get that algebraically by taking 1 and subtracting 2 from its y value. You'll get -1. So I can see that this parabola does in fact open up, as I would anticipate for a parabola whose leading coefficient of x squared is +1. And you can even find the x-intercepts by letting y equal 0 if you wanted to get a precise graph. But for just a sketch, I'm going to just do a quick sketch of a parabola opening upward like this. Again, yours could be much cleaner than mine, hopefully. There we go. All right. So that's a basic sketch of a parabola opening up with those 3 key points. Okay. Now for shading, as far as shading is concerned, we need to test, don't we? So who can I test that is not already on that parabola? 0, 0 works for me. So if I put 0, 0 in for x and for y for the first constraints inequality, I would have 0, so I'm testing 0, 0. I would have that 0 must be greater than or equal to 0 squared minus 2. In other words, 0 must be greater than or equal to -2. Is that true or is that false? Is 0 greater than negative numbers? Yeah, it is. Since it's true, I include 0, 0, which is above the parabola, or inside the parabola if you prefer. So I'm shading above, or if you like inside better, feel free to write it that way. I'm shading above this parabola, or inside the parabola. Okay, now we're heading over to our second constraint. It's a lot nicer for many of us. This constraint is a what? Y is less than x plus 4. That's a line, isn't it? Hey, would this line be solid or dotted? Meaning, do I include the points on the line as my solutions or not? I would not include them. This is a dotted line because it's strictly less than the line. Okay, so what do we have here? We have a line in slope-intercept form where its slope is the coefficient of x, 1, so +1 over 1, or you could also go -1 over -1. That also gives you 1. And the y-intercept is +4. So starting at 4, 1, 2, 3, 4, the point 0, 4, right there, I'm going to now travel up 1, right 1, up 1, right 1, and I keep going like that until I stumble upon the parabola. You can estimate where it is, but I would not trust my graph because, as you can tell, I was very, very not cautious as I drew that parabola. Also, I would go down 1 and left 1 from the y-intercept. So down 1, left 1, down 1, left 1. Maybe somewhere around here is crossing. And you could keep going like that to even show what your x-intercept would look like. Down 1, left 1, down 1, left 1. So an x-intercept does appear to be at -4. Okay, so drawing that dotted line, meaning I do not include points on that line for my solution region, it's more of a boundary. So these would be the boundary markers for that constraint. Okay, so we have our parabola and we have our dotted line. Now we have to talk about testing, right? Test points for shading. So we already tested 0, 0 on the parabola. Can we use 0, 0 for this line? Yeah, it's below the line. We can do that. So if I test 0, 0 for the line, what happens in the inequality? I would have y is 0. Is it less than 0 plus 4? In other words, is 0 less than 4? Yeah, it is true. And if that's true, I include the point. So including 0, 0 would mean shading where 0, 0 is located in relation to this line. That's below the line. So I'm shading below my line and above my parabola. To shade above the parabola, we're in this region, all of this region, right? But now to only be shading below the line, wouldn't that just be this space? Not doing a great job, but you get the idea. So any of these spaces would be correct. Well, now I'm just coloring for fun. So what I want to point out to you is that any point in this region is a solution, including on the parabola itself down here. Those are also points that are solutions. But notice what are excluded from the solution region. Now I just got really into coloring, sorry. Okay, what are not included? Let's get our blue pen again. These boundary points, those are not part of the solution. those are dotted, that's a dotted line. So the only solution would actually be including the parabola part down here. So this part down here, these are included in the solution. But the blue dashed line is not included. Okay, so that would be what we call our solution region. Now to finish off this question, you need to know where the vertices are. And the vertices are those points of intersection which do in fact trap the solution region. So how do we find points of intersection besides just guessing? We don't want to guess. We need substitution or elimination using the system of equations. So the first equation, if you wrote it with an equal sign, would have been y equals x squared minus 2, the parabola. The second equation would have been y equals x plus 4. Go ahead and solve that system using substitution or elimination. Both of them would work this time. Let's see how you did. I probably would have just done substitution, replacing y with whatever this expression for y is. So I would have on one side x plus 4, and on the other side x squared minus 2. If you had done elimination, you just would have to eliminate the y's, but not the x squared. So it would become x squared minus x minus 6 on one side. So let's see what happens if you get 0 on the left here. You would have x squared. You'd move over the x as a negative x, the 4 as a negative 4. Negative 2 minus 4 is negative 6. So you should get the same result either way. Now, again, we've seen this trinomial a few times in our video series recently. So we can factor this trinomial and get x in each of the binomials. The factors of negative 6 with different signs that add up to negative 1 would be negative 3 and positive 2, producing x equals 3 and x equals negative 2. Now we have two places, 2 points of intersection. When x equals negative 2, that must be this one here, like negative 1, negative 2, something like that. So this is x equals negative 2. And x equals positive 3 would be like 1, 2, 3, right here, isn't it? So that's x equaling 3. So we're seeing here that our points of intersection would be negative 2 something and 3 something. How do I know exactly where the y value is? I plug those x's into one of the equations. But which one? That's right, into the one with the smaller power, so into the line. So if you take 3, for example, and replace x with 3 in the linear equation, you'd get y equals 3 plus 4. So y equals 7 when x equals 3. So this is this point. Similarly, if you replace x with negative 2 in the second linear equation, you would get y equals negative 2 plus 4, which is positive 2. So when x is negative 2, y should be positive 2. That appears to be happening, right? Doesn't it? So now we have labeled our points of intersection, and we can answer the question, what are the vertices of the shaded region, of the solution region? They're the points of intersection which do in fact trap the shaded region. So in this case, your vertices are just those same 2 points. But sometimes they'll be just some of those points. So we have to be careful to distinguish between any points of intersection and those specific points of intersection which trap the shaded region called vertices. All right, I believe we have one more example for you to try on your own. Here we go. This system has as its first constraint, x squared plus y squared must be less than or equal to 25. And as your second constraint, y must be greater than or equal to x squared minus 5. See how you do. Okay, the first case, did you get a circle? I hope so. Is it a solid circle or was it a dotted circle? It was solid, good job. And what was your center? Yep, it was 0, 0. Good job again. They're not always this nice, but we're trying to get you comfortable with the process. What was your radius? Yep, it was 5. So a circle centered at the origin, 5 units away from it to be a point on the circle. So starting at the origin 0, 0, I'm going to go up 5. 1, 2, 3, 4, 5. That's at 0, 5. Right 5. 1, 2, 3, 4, 5. That's at 5, 0. Down 5. 1, 2, 3, 4, 5. That's at 0, negative 5. And left 5 from the origin 1, 2, 3, 4, 5. That's at negative 5, 0. Okay, draw your solid circle as well as you can. Again, if you had a compass and a protractor, this would be so much better. You get your perfect circles. And they sell those at the store. They're only like $5 or $6 if you want one. Okay, so we have a basic sketch of our circle. So from here, what do? Well, we talk about shading. Am I shading points inside the circle or am I shading outside the circle? So I pick a point to test. Any point that is not on the circle. You know my favorite, it's 0, 0. 0, 0 is not on the circle, so I can test there. That would mean 0 squared, which is 0, plus 0 squared, which is 0, must be less than or equal to 25. Is that true or false? Is 0 less than or equal to 25? Yes. Therefore, I include the point 0, 0, which happens to be inside the circle. So I'm shading inside my circle. So right now, to be a solution, you're any point inside of that circle and you're on the circle. Okay, let's hit our second constraint right now. Our second constraint was that y is greater than or equal to x squared minus 5. What kind of constraint was that? That was a parabola. Good job. We've done a few of these in our video series recently. This is a parabola shifted down 5 units, so our key points would be at -1, but instead of 1, if you go down 5, you're 1, 2, 3, 4, 5, you're here. That's the location of -4, isn't it? Instead of 0, 0, we'd be at 0, -5. So that's down here. Ooh, did we just stumble upon a point of intersection? We may have. So 0, -5 appears to be a point of intersection. We'll verify. Also, the third point, 1, 1 is now at 1, -4 for the same reason as -1 was. It moved down 5 units right there. So would this graph be solid or dotted? It is solid. We would include every point on the parabola in the solution region. So again, if you wanted a better sketch, you would go ahead and actually go through the work of letting your y values equal 0 to find those x-intercepts, and you'd get a much cleaner and correct sketch. Right now, we're just basically just saying go up. Okay. All right. Now that we've done that, we need to talk about shading and vertices, right? So let's discuss shading for the parabola. Who should we test for this parabola? Well, I could test 0, 0 again, because 0, 0 is not on the parabola itself. So that would mean in the second inequality that 0 would have to be greater than or equal to 0 squared minus 5. In other words, 0 would have to be greater than or equal to -5. Is that true or is that false? Is 0 greater than negative numbers? Yes, it is. So since that's true, I include the point 0, 0, which happens to be where in regards to the parabola? It is in fact inside of the parabola. So inside or above, however you like to write that. So we now know where to shade. We're shading both inside the circle and above or inside the parabola. So wouldn't that be this region here? Inside both of them at the same time? So that would be the region. You could completely fill it in. Any point in that region is correct, as well as any point on the top part of that circle and this part of the bottom part of the parabola. All of those points would be solutions. But as far as the vertices are concerned, points of intersection which trap the shaded region. Again, this time it looks like all 3 points of intersection are trapping the shaded region. So once you found all 3 points of intersection, they will also inform you of all 3 vertices. Okay, so that's not always the case. I know you got the idea from my video today that it's always the same, but most of the time you're going to have many more points of intersection that do not trap the shaded region. We ignore those when we're discussing vertices. Okay, so to find the formal points of intersection, we think we know where they are from the graph, but we want to know for sure what those points of intersection are. So to do that, we do our substitution and elimination one more time. Feel free again, if you haven't paused it yet, to pause the video now and make sure these skills are solid. Your first equation was x squared plus y squared equals 25, and your second equation was y equals x squared minus 5. So if I was doing substitution or elimination here, elimination would definitely work to eliminate the x squareds, but not the y squareds, so just be aware of that. Also, I probably wouldn't want to replace y, but rather x squared, so that I don't get y to the 4th power, right? So if I got x squared by itself, I'll use substitution for kicks and giggles here. In the second equation, I would have x squared on one side equaling y plus 5 on the other. Just getting x squared by itself. Then I would replace x squared in equation 1 with y plus 5. So I'm doing substitution there. I get y plus 5 plus y squared all equals 25. That would mean, if I rewrite it as a descending order trinomial, y squared plus y. I had positive 5 on one side and positive 25 on the other. If I subtract 25 to get 0 on one side, I would have 5 minus 25, which is negative 20, equaling 0. That factors nicely. What are your factors? That's right, y plus 5 and y minus 4, creating 2 answers for y. Either y is negative 5, which does make sense in our first point of intersection, so y could be negative 5, or y could be positive 4. Now, where would I plug those into? Into the parabola or the circle? Into the parabola, correct. In fact, the way I'd probably do it is into that nicer version of the parabola, which already has x squared by itself. So if you had plugged in -5 into that version of it, you'd have -5 plus 5, which is 0. 0 equals x squared, so x must be 0. We already got that one. Great. What about if we put 4 in for y there? 4 plus 5 is 9. So if x squared equals 9, what are my options for x? That's right, x would be positive or -3. So I would have plus or minus 3 whenever y is the number 4. So this is positive 3, 4, and this is -3, giving you 4. So our vertices, again, happen to be the same as our 3 points of intersection, 0, -5, -3, 4, and positive 3, 4. And because those 3 points of intersection trap the shaded region, that's why we call them the vertices. All right, so again, this is going to be a skill which is really helpful going forward in your math classes, but also in a whole branch of mathematics alone, which is called operations research. Businesses use this type of math behind the scenes to figure out where to set their price point and what to order. All right, so at this point, it is up to you to practice because math is not a spectator sport, and I'll see you next time.